In this video, we're going to cover some common families of graphs. In particular, we're going to look at complete graphs, bipartite graphs, regular graphs, paths and cycles, and hypercubes. The first graph we're going to talk about is the complete graph. The complete graph is a graph that, given any two vertices in the graph, those two vertices are connected by an edge. In other words, every possible edge is in the graph. This graph is denoted by a capital K and a subscript n, where n is the number of vertices in the graph. So, for example, below in figure 1.2.1, the K1 means we have a single vertex, and the K2 means there are two vertices, and of course those two vertices are connected by an edge. The K3, three vertices, and every vertex is connected to every other, and so forth. The next special class of graphs that we're going to define is the bipartite graph. The bipartite graph is a graph whose vertices can be partitioned into two sets, with the property that any two vertices in the same set are not adjacent, so there are no edges induced in either partite set. And all of the edges in the graph, therefore, have one edge or one vertex in one set and one vertex in the other partite set. We've seen this example before, where we label the two partite sets U and V. If we put these two definitions together, there's something called a complete bipartite graph. First of all, it's bipartite, so we can still partition the vertex set into two sets where there are no edges in either set. But since we're calling it a complete bipartite graph, that means given any vertex in one of the partite set and any vertex in the other partite set, that edge is in the graph. We denote the complete bipartite graph by a capital K, like we did with the complete graphs, but instead of having just one subscript, we have two. So we have n comma m. The first graph in the right-hand column, G1, is a K, 2, 3, since we have two vertices in one partite set and three in the other. The second example, G2, is a K2, 5. Our next graph is what is called a regular graph. A regular graph is a graph where every vertex has the same degree. We call these K-regular, where K denotes the degree. So, for example, Peterson's graph, since every vertex has degree 3, this is a 3-regular graph. A path is a special class of graphs, and a path is a graph in which all of the vertices can be drawn in a straight line such that there's exactly one less edge than there are vertices. So the result, as we can see in the right-hand column, if you have a path with two vertices, you simply have an edge, and a path with three vertices would be two edges. A path with four vertices would be three edges, and so forth, so you have exactly one less edge than you have vertices. We denote the path with capital P sub n, where again the subscript is the number of vertices. The cycle graph we denote with capital C sub n. In the cycle graph, the vertices can be drawn in a circle or in a cycle, and in this case, the number of edges equals the number of vertices. Which makes sense because if we take the path graph and add one more edge, connecting the last vertex to the first vertex, if you want to think of it that way, we generate a cycle. So in the right-hand column, as you see, is a cycle of length 6 with 6 vertices and is denoted by C sub 6. Before we continue with the different types of graphs, I think it's important to note that it's not how you draw the graph that defines the graph, but rather how the vertices are connected by the edge set. So for example, if we look in the right-hand column, there are 3 different graphs. Or are there 3 different graphs? So let's see. If we look at the first one, it's a graph on 4 vertices, first in the sense of going left to right. We have 4 vertices, and each vertex is of degree 3. So it's a 3 regular graph. But in addition, given any vertex, there are only 3 remaining vertices. So this means that every vertex is connected to every other vertex. So this is a drawing of the complete graph on 4 vertices, or the K4. Now when we defined the complete graph and we looked at a K4, we looked at the representation given in the middle graph. So the first graph and the middle graph are actually the same graph. How do you know that whether 2 graphs are the same? In general, that's a very difficult question, but in many cases, especially for small graphs, you can tell. So if we look at the third graph, the graph on the right, notice that there is a vertex of degree 2 and a vertex of degree 4. So this is not the same graph. But again, you can draw a graph a number of different ways. So as our final example then of this discussion, we had the cycle of length 6, or the C6, as in the first drawing here. Down below, we have another drawing. In both cases, we have 3 red vertices and 3 blue vertices. So the question is, are these 2 the same? So we'll save the answer to this for our discussion board. You can review this page and see if you think these are the same graph or if they're a different graph. Our final special class or family of graphs for this video is the hypercube. Now the hypercube for any n has 2 to the nth, or 2 to the n vertices. So if n is 1, there are 2 vertices. If n is 2, there are 2 squared, or 4 vertices. If n is 3, it's 2 cubed, or 8 vertices. So if n is 4, how many vertices would the hypercube have? 2 to the 4, or 16 vertices. So we know how many vertices there are for each n. Now for a given n, there are 2 to the n distinct binary streams of length n. So for example, when n is 2, there are 4 distinct binary streams of length 2. 0, 0, 0, 1, 1, 0, and 1, 1. So that's why we have that many vertices. We want to label each vertex with a binary string of length n, or when n is 2, we want to label each vertex with a binary string of length 2. Now that the vertices are labeled, this helps us determine where the edges are. If two binary strings differ in just one position, we want to put an edge between those two vertices. So for example, 1, 0 and 1, 1, they differ in the last position only. So there's a connecting edge. However, 1, 0 and 0, 1, those two differ in two places. They differ in the first position and they differ in the last position. So there's no diagonal. Also, 0, 0 and 1, 1 differ in both places, see, so there's no diagonal. But 0, 0 and 0, 1, they differ in the last position only, so there's an edge. So once we have our vertex set, if there's a well-defined way to determine the edge set, then we've completely defined the graph. So the hypercube, again, has 2 to the n vertices. Each vertex is labeled with one of the binary strings of length n. And then there's a connecting edge if those two binary strings differ in just one place. So we have now covered the following: a complete graph, which is a graph in which every possible edge is in the graph, a bipartite graph, a graph with the property that the vertex set can be partitioned into two sets where there are no edges in each set, regular graph, where every vertex has the same degree, paths and cycles, and finally, hypercube.